Good evening, everyone. Welcome to the session where we discuss practice problems. So, today we'll be discussing practice problems from week three's content. Um, for a brief introduction, I am one of the TAs for the NPTEL Natural Language Processing course, and we'll get started with today's session. The first question is: which of the following words contains both derivational as well as inflectional suffixes? Regularity, carefully, older, availabilities. In order to identify derivational and inflectional suffixes, we first need to understand derivational and inflectional morphology. What is inflectional morphology? So, when a word is inflected, uh, so the core meaning which is associated with the inflected form of the word and the original word, the root of the word, that remains intact. It's retained. There's no major change in the difference of the core meaning that is associated with the inflected word form. Also, one more observation is that the category or the part of speech category stays the same. There's no change in the part of speech tag category of the inflected word form and the root form of the word from which it was derived. So let's take an example. Um, for example, the word cats. The word cats was derived from the root word cat. So here we observe that both the root form of the word, that is, that is cat, and the inflected form of the word cats have the same part of speech tag category, which is noun. Here we are simply adding the plural suffix marker s, which is an inflectional suffix, which simply changes the number of the word. So cat is a singular form and cats is the plural form. So the only change is the number that is marked on the noun that has changed, and this is an example of inflectional morphology. And so this s that we are adding, the plural marker, is an inflectional suffix. Okay, uh, so that is an example. Another. So now let's talk about derivational morphology. So in derivational morphology, there are two distinct changes that we observe in contrast to inflectional morphology. So in derivational morphology, the major contrast is that after the word formation process, so the derived word form and the original word form, the root word form, there is a change in meaning. So, for example, let's take the word writer. The base form of writer, the root from which the word writer was derived, is write. So, write is a verb uh, which means the action of performing. It means the action of writing. Whereas writer, which is a noun form, it means a person who is writing. So, so there's a change. So, so there's a substantial change in meaning that is happening. Also there's a change in part of speech tag category that you can observe in derivational morphology. So here the suffix that we added to write er, that is a derivational suffix because it is inducing a substantial change in meaning, um, and also it is changing the part of speech tag category. So these, so this is so this is what is so this is how we describe derivation and inflectional morphology. So now that we have understand these points, we can try solving this problem. So let's take the first option, that is regularity. So regularity uh, is a word form that is derived from the word regular. Regular is the root of this word. Now, ity was added Ity is the suffix that was added to regular to make it regularity. So now we need to identify whether ity is a derivation or an inflectional suffix. So how do we identify that? Based on what we discussed. So regular, the root form of the word regular, it is an adjective which uh, which indicates us that is something uniform or consistent. Whereas regularity is the noun form of the word, which indicates the state of being regular. So here and also regular, the root form of the word regular, that is an adjective, whereas regularity is a noun. So here you observe that there's a substantial change in meaning associated, and there's also a change in the part of speech tag category. So here we can conclude that ity is a derivational suffix. Now let's discuss about the second option, which is carefully. So carefully is a word form that is derived from the root word careful. So now again we need to identify whether there are any derivation or inflectional suffixes. We observe that there is a suffix which is li. So careful, careful is an adjective. So whereas when I say carefully, carefully is an adverb. So it is very common that you add the suffix li to change to derive an adverb from an adjective. So here again there's a change in part of speech tag category. And so carefully, when you add the suffix li, it also means the manner of performing something. So so that is why this is in so that is uh, so so that here's again a change in meaning that we are observing here. So that makes li a derivational suffix. Now let's take option 3. Here we have the word older. Here is the suffix that is present. So this is the comparative. So old is from old to older. So older is a comparative word form of old. Here again, would be a derivational suffix. Now let's take the last option, which is availability. Still now in none of the options we have come across an inflectional suffix. So let's analyze the last option, which is availabilities. So in availabilities, the root word is avail. So avail is a verb, and it means to um, there's a verb which means that um, so I can we say that we can avail avail some opportunity or some chance. So avail means to use something or utilize something. So and when we add able to it, we get available. Okay, so available is an adjective. So here we observe that when we get available, when we go from avail to available, there's a change in part of speech tag category the along with there's a change in meaning. So able over here would be a derivational suffix. Then now that we have available, next we add the suffix ity to get availability. Again, availability is now a noun. So ity would be a derivational suffix again. So so here we have two derivational suffixes. Finally, we can add es, which is the plural marker, so we go from availability to availabilities. So we're getting the plural word form. So here es would be the inflectional suffix. So this word availabilities has both derivational suffix as well as inflectional suffix. So just to reiterate, here in availabilities, avail is the root word, able and ity are the derivational suffixes, and s, that is es, is the inflectional suffix. So this is the so here from here we can understand that the solution of this problem is option 4, that is availability. So here one thing to observe over here is from going from avail to available, there was a change in part of speech tag category. Away from available to going from availability, there was again a change in part of speech tag category. However, when we had availability, to go from availability to availabilities, there was no such change. Okay, this is just to highlight that based on our previous discussions on what is derivation and inflection morphology, we can clearly identify which are the derivation and inflection suffixes present. Now we'll discuss the next problem. So here question 2 is, let's assume the probability of rolling 2 times in a row of a dice is P. Consider a sentence consisting of n random digits. A model assigns probability to each of the digits with probability P and the perplexity of the sentence. The way we need to solve the problem is we need to start by computing P. So P is the probability of rolling 2 times in a row of a dice. Uh, so it is the probability of consecutively getting 1 in in a row of a die. So the probability will be 1 by 36. Why? Because the probability of getting 1 uh, on a dice roll is 1 by 6, and probability of getting 1 on another dice roll is again 1 by 6. Now both of the roll of dice, they're independent, so we can simply multiply the probabilities. So 1 by 6 into 1 by 6, we can simply multiply the probabilities, and we get 1 by 36, which is the probability of rolling 1 probability of rolling 1 2 times in a row of a dice. We get 1 by 36. One thing to mention is that in the roll of a die, the possible outcomes are so either we can get 1 or 2 or 3 or 4 or 5 or 6. So there are 6 possible outcomes. Each are equally probable. Because of that, we get the probability of getting 1 in a single dice roll to 1 by 6. And then, as I mentioned, we have two rows. In both of the rows, I'm getting 1, so it's 1 by 6 into 1 by 6. Now, instead of 1, if there was some other number, say uh, rolling of getting 2 in 2 times in a row, in that case also we would get the same value, 1 by 6 into 1 by 6 itself, because each of the outcomes are equally probable. Also, if the question was what is the so on one roll of a die you get 3, on another roll of a die you get 5. Now if that was the probability that was assigned, in that case also it would have been 1 by 36 only. So in that case also it would be probability of getting 3 on a single dice roll into probability of getting 5 on a single dice roll, and both of them have value 1 by 6. So for all such possibilities, the probability would end up being 1 by 36. So now that we have computed the probability, uh, let's uh, let's read the remaining problem. So here we are told that consider a sentence consisting of n random digits. So we are given a sentence which has n random digits, and the model is assigning a probability to each of the digits, and the probability value is p, which is the value we just computed, which is 1 by 36. So each of the random digits have probability value of 1 by 36. Now, in order to calculate the probability of the perplexity of the sentence, what do we need to do? The first we need to compute the probability of the sentence. What would the probability of the sentence be? It would be the probability of the n digits that it constitutes. So we will have 1 by 36 to the power n, capital N, because capital N is the number of random digits that are there. Now for perplexity, what is the formula of perplexity? We'll just check over here. The formula of perplexity is we simply then normalize. So we take the inverse of the probability, and we normalize with the number of words. So that is why we have this. So 1 by 36 to the power n, which is the probability of the sentence that we just computed. And now we take to the power of minus 1 by n, and when we do the computation we get 36. So this is the answer to this question. So to briefly discuss one small point of what is perplexity of a language model. So perplexity is um, perplexity is an intrinsic measure of measurement of how good a language model is. So, uh, to briefly explain it, it measures the degree of perplexity, confusion, or uncertainty that a language model has at any time step when it is generating a new token. Uh, so, since perplexity is associated with the confusion that a model has, so lower the perplexity value, the better is the language model. So yes, so it is like as I mentioned, it is an intrinsic evaluation metric, and it helps us determine the quality of the language model. Um, Maybe we can take one small example that was discussed in the slides. Uh, just a second. So let's take this example. So the intuition of perplexity can be best explained with the Shannon game. So what happens in Shannon game is that we ask the question, how well can we predict the next word, or how well, say, a language model would be able to predict the next word. So here, let's take the first sentence. I always order pizza with cheese and dash. Or so here the model needs to predict the next word. So here we expect the model to generate words which are valid and legitimate, and which would go well with the context of the sentence. So for example, um, I always order pizza with cheese and cheese and paneer. So that is a valid sentence. Whereas if I say I always order pizza with cheese and say orange, that doesn't seem like a legitimate word that can occur in this context. So that is what perplexity measures. Um, so so yes. So I think that So I think so. I think the understanding of perplexity is now. I hope you all can understand what perplexity is. It was there in the video lectures as well. I just thought of explaining it once since it is related to the problem statement. So so I hope it's okay. Just one more notion that is related to perplexity is over here. So I just so that is this is what I was searching for. So here we observe this is similar to the question that we had. So here we have n random digits, and here we are trying to find the perplexity of a sentence as per a model that assigns a probability of 1 by 10 to each digit, right? So the perplexity of the word, perplexity here W is the entire, so the corpus which consists of capital N words. So we take the probability and then we do the inverse of the probability and then normalize it with the number of words that are there. So that gives us, so we do the computation 1 by 10 to the power capital N, and again that to the power minus 1 by n. Finally, we get the value of 10. What does this mean? This means that when the model is predicting the next digit, it has 10 possible options to choose from. That is what it means. So, uh, so that is the perplexity of 10, perplexity score of 10. That is what it means. Okay, we'll go over to the next question. Now the third question is, assume that X represents the input and Y represents the tag slash label. Which of the following mappings are correct? So here we need to understand what are generative and discriminative models. So even generative and discriminative models were also covered in the lecture videos. We just still just discuss them once. Okay, so let's discuss about generative models. Generative models are also called joint models because they are because because like because they use the joint probability. So they use probability of x comma y. So generative or joint models. So here what we do is we generate the observed data from hidden variables. So here what we do is we put a probability over the observations given the class. So here we here we here we learn from the joint probability. So and we also make use of Bayes rule over here where we compute probability of y given x. So that is what happens in generative models. So some examples of generative models would be naive Bayes, hidden Markov model. All these are examples of generative models. Okay. And similarly, if we talk about discriminative models, so here what we do is we directly compute y given x. So here we take the data to be given to us and then we put a probability over the hidden structure or the hidden states given the data. So some examples of discriminative or conditional models would be logistic regression, maximum entropy models, conditional random fields. So the answer in this case would be options 1 and 4. So I'll just simply read over the solution once, just to reiterate what I just said. So generative classifiers learn a model based of the joint probability P of x comma y and make their predictions by using Bayes rule to calculate probability of y given x. Discriminative classifiers, they model the procedure probability of y given x directly, or they learn a map from the inputs x to the class labels y. So this is the difference between generative models and discriminative models. So generative models, they walk or they learn the joint probability directly, whereas discriminative models, they learn the posterior probability of y given x directly. So option 1 and 4 are the correct answers. So we'll discuss the next problem. So this is an extension of the previous problem. The question 4 is, which of the following is an example of the generative model? And the options are conditional random fields, naive Bayes, support vector machine, logistic regression. So as we discussed in the previous question, the answer is option 2, naive Bayes, an example of generative model. Some other examples of generative model would be hidden Markov models as well, which are also a part of this week's content. So, so these are some very common examples. So naive Bayes and hidden Markov models, these are some very common examples of generative models. And so in generative models, we learn from the joint probability. So probability of x given x comma y, where x is the input, y is the output. And all the other models that are present here, so conditional random fields, support vector machine, logistic regression, all the other models that are given in the option, there are discriminative models. So what happens in discriminative model is that they directly compute the posterior probability of y given x, and so yes, so that is the discriminative models. We'll discuss the next problem. So question 5 is, which of the following morphological processes is true for motor plus hotel to motor? And the options are suppletion, compounding, blending, clipping. So let's discuss each of the options first. So um, each of the options are a type of word formation process. So let's try and understand what each of the processes are, and then we can arrive at the answer. So, so what is suppletion? So in suppletion, we find irregular word forms, so such as go to went, good to bitter. So in regular English grammar, uh, to 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 go to the past tense form of a word, we simply add the past tense marker suffix ed. So, for example, take the word dance. Dance plus ed, danced, is the past tense form of the word dance. So, this is a regular example. This is a regular verb because it is following the regular grammar rule. Whereas if we take go to went, here we observe that went is the past tense form of the word go, but there's no ed suffix. So go plus ed would be goed, Goed, which is not a valid word in English. So here to get the past tense form of the word, we cannot simply add ed and get it. So it is completely different. It is an irregular word form. So here went is the regular verb form, and this is an example of suppletion. Next is compounding. So what happens in compounding is we uh, simply take some words, two or more words, and combine them to form a word. So an example of that would be um, example of that would be so just a second. So yes, the example of that would be say ice cream. So here ice is a word, cream is a word. We combine them to get the word ice cream. Some other examples would be say bittersweet. So here bitter is a word, sweet is another word. We combine them to get bittersweet, which is an example of compounding. Next is blending. So what happens in blending is we simply combine two words, but the catch is it is different from compounding because after the two words are combined, it is difficult to identify what were the um, original constituent word forms that were combined to get the final word. So, for example, let's take breakfast plus lunch is brunch. Here, from the final word brunch, you cannot isolate the initial words breakfast and lunch, which were combined to form the final word. So here brunch is an example of blending, whereas when we talked about compounding just a while back, so compounding there also we were combining two word forms and we're getting a combined word. Say ice plus cream is ice cream, but in ice cream you can isolate and you can identify what were the original word forms. Like ice and cream were combined to get ice cream, so you can identify the original word form. So that is possible in case of compounding but not in case of blending. And finally, let's discuss about clipping. So what happens in clipping is that so if you have a long word, we simply shorten it, we simply clip it. So an example of that would be so we use the word add as a clipped form of the word advertisement. So advertisement is the original word. We clip it and we get ad. So that is an example. Um, so all these are examples of different word forms. There were a few more word formation processes that were covered in the slides. Um, Maybe we can discuss them as well. So So, one is that of reduplication. So in reduplication, we observe that a part of the word or the entire word gets duplicated. So, for example, let's take the word basa in Tagalog. So this is an example from the slides only. So the word basa in Tagalog means to read, and so ba basa will mean will read. Also, we can take the example in Hindi, like Diwali घर घर में मनाई जाती है. So here we observed घर घर. घर is being repeated twice. So घर means somebody's home. घर घर means in everybody's home Diwali is celebrated. So that is also an example. So these are the main things. We also discussed derivation and inflectional morphology in the beginning. I think one thing that I did not mention maybe was that with the inflectional morphology, there are some grammatical features associated, namely that of number, tense, case. All these things are associated with inflectional morphology. So even the example that I gave of dance to danced. So here this is an example of inflectional morphological process. So ed is an inflectional suffix. And um, so yes, and so all these things that we discussed till now, so these are various word formation processes. But now, how do we deal with morphology? So for processing of morphology, we have different processes such as lemmatization, and so all these things are done to take into account to process morphology. So those are not morphological processes or word formation processes. Those are just techniques that have been put into place to process morphology. So we know in lemmatization what happens is we simply take the word, and after the process of lemmatization we get the lemma. Um, so for example, we're talking about danced, right? So after performing lemmatization on dance, we'll get back the lemma dance. So, lemmatization and stemming were also covered in the previous live sessions. Um, just for a recap, I mentioned. Um, so, based on this discussion, now I think we can answer this question. So, here we have motor plus hotel motor. So this is an example of blending. So blending combines parts or two parts of words. That is the example. Um, before going on to the next question, we can discuss a few things. So let's discuss one thing from the slides that is important. Yes, so let's discuss how do we process morphology. Hmm. Okay. So here we observe first is we have lemmatization, where we go from the word to the lemma. So that is what we discussed. So that is lemmatization. So we start if we start with saw, after lemmatization we can have see and saw, which are the lemmas. Another thing is that at morphological analysis, what happens in morphological analysis is that um, so let's see the example first. So when we do morphological analysis of saw, so so saw can be two things. One is it can be the past tense form of the word see. So in that case, saw can be a verb. When saw is a verb form, it is the past tense verb form of see. So uh, when I do morphological analysis, keeping in mind that saw is a verb, we get this. We get see is the base form, and it is a verb, and it is in the past tense form. So this is what we obtain about on morphological analysis. Whereas a saw could also be a noun. So it is an instrument, I think, not an instrument. I think it's used to cut trees. So there it's a noun form, and it is a singular noun form. So here we see that saw can be interpreted in two ways, and based on that we can have two possible morphological analysis. So that is what, so this would be the lemma. First part is the lemma. The remaining part is the tag. So the morphological tags. So one is it consists of the POS tag, and it also contains the features. So what is the tense? What is the number? So here verb dot past means past is the tense, whereas when I'm talking about the noun form of the verb, SG means it is singular. Okay. What is the next morphological process? It is that of tagging. So let's see this example. Peter saw her. So in Peter saw her, we are for the so our word. So the word that we are concerned about is saw. Here we take into account also the context, and because of that, we now understand that here saw is being used as a verb and not as a noun. So we can clearly state that in this case, after morphological analysis, we'll get this. Sorry, this to be uh, this to be the solution. This so here since it is saw is a verb over here, so the lemma would be see, and it is a verb, and it's in the past tense form of the word. We could get rid of the noun form of the word by using the context. So um, by using the context, we could get rid of the ambiguity that was present. Um, another another way of processing morphology is morpheme segmentation. So what happens in morpheme segmentation is that, so if we are given the word denationalization, upon morpheme segmentation, we would be able to get the constituent morphemes. So here D, DE, is a morpheme. Nation is again a morpheme. AL, IZ, and Asian, all of these are morphemes. Nation would be the root word. DE would be a prefix, and all of these AL, IZ, and Asian, all of these are suffixes. So upon morpheme segmentation, we obtain this. Now, what is generation? What happens in generation is that we supply the lemma, which is C, and then we also say that what are the morphological tags. So it is verb and past tense. So by, upon being given this morphological information, we can generate the corresponding word, which is saw in this case. Okay, so here we are generating the morphologically inflected word form given the lemma and the details about the morphological tags. So just checking if there's anything related that we can discuss. Just a second. So we discussed the different word forms, right? We discussed the different word forms. Sorry, not word forms, word formation processes. We discussed those. Reduplication. So reduplication is observed in many Indian languages. However, it's not that common in English, but it is quite frequently observed in Indian languages. Um, okay, we'll go over to the next. We'll go over to the next question. So in question 6, what we have is consider the HMM given below to solve the sequence leveling problem of pure stagger. So with that HMM, consider the probability that the sequence of words free workers will be assigned the following parts of speech VB and NNS. Here we are given a table containing all the emission probabilities, and this diagram contains the transition probabilities. So how would we solve this problem? So one thing to note over here is free workers, the sequence of word free workers, it could have many possible parts of speech. So if we can even try to enumerate all possible such cases, but here in the question we have only been asked about VB NNS. Uh, what is the probability if the sequence of words free workers will be assigned the parts of speech VB and VB NNS. Let's discuss the solution. So here probability of uh, so here what is the probability of the sequence of words free workers being assigned the probability tags VB and NNS. So here what we do is, so here it is the product of these probability terms. So so this is a problem based on HMM, and HMM, as we learned, it's a generative model. So there we have the tags. We start with the tags, and based on that, the words are emitted. So here again, so here from this here, so first we start from the starting state, and then we make a transition to the tag VB. So here the first probability term is the transition probability of transitioning from the start state to the VB state. Now once we are at VB state, now we need to compute the probability that what is the probability that this tag or this hidden state VB will emit the word free. So that is this probability of free given VB. So this is the emission probability. Next, next that now we are at the state of VB, we'll transition next to NNS, which is another hidden state, which is another tag. So here we have the transition probability of NNS given VB, which is the probability of transitioning from state VB to NNS. Now, once we are at the NNS state, we need to ask what is the probability that the NNS state will emit the word workers. So that is this probability of workers given NNS. That is the probability. And finally, once we are over here, once we are at NNS state, we make the final transition from the NNS state to the N state. Um, so then we simply multiply the probabilities and we get the final answer. We'll just check how these values came about. We'll check the diagram below in the previous slide. So what is the probability of VB given start? As I mentioned, it is the probability of transitioning from the start state to the VB state. So from where can we obtain that value? From here. So here we are transitioning from start state to VB state, and this arc has a probability of 0.25, and that is the probability value of probability of VB given start. Okay. So all the transition probabilities are there in this diagram. Next is probability of free given VB. This is an emission probability. And emission probabilities are present in this table. So, so it is a probability of free given VB. So what is the probability that the tag VB will emit the word free? So that is this, the 0.00123. So that is the probability of free given VB. This is the emission probability. Next is probability of NNS given VB. What is this? This is again a transition probability of transitioning from VB to NNS. We again check the diagram, VB to NNS. VB is here, NNS is here. So this arc, the probability that is marked on this arc. So this is 0.85. So we have 0.85. Next is probability of workers given NNS. From where can we get that? This is again an emission probability. So probability of workers given NNS. What is the probability that the NNS tag will emit the word workers? So this 0.000475. This is the emission probability value in this case. And I think the final was we make the transition from the NNS state to the N state. So NNS state is here, the N state is here. So this is the probability 0.4. So so we just multiply all the transition probabilities and all the emission probabilities, and with that we get the answer. Um, Next, let's discuss the seventh problem. The seventh problem is which of the following is or are true? The option 1 is only a few non-deterministic automation can be transformed into a deterministic one. Option 2 is recognizing problem can be solved in linear time. Option 3 is deterministic FSA might not contain empty epsilon transition. Option 4 is there exists an algorithm to transform each automation into a unique equivalent automation with the least number of states. Okay. So this is a very direct question. I don't think there's much to discuss here. So I'll just read the solution, and um, from that we can understand the 2 and 4 are the answers. So what is the solution? So every non-deterministic automation can be transformed into a deterministic one, and a deterministic FSA should not contain empty transition. So this is the solution, and the answers are 2 and 4. So let's discuss the last practice problem. The last practice problem is which of the following are an example of clipping? And there are different options given. We discussed clipping a while back, so this uh, this problem would be easy. So here the answers are 2 and 4. So gator is the abbreviated form of alligator, and ad is the abbreviated form of advertisement. So both of these are clipped forms. Maybe one thing we can discuss further on clipping is clipping can be of multiple types. Maybe we can discuss that. Let's see. So one type of clipping is back clipping. So an example of back clipping would be gym. So we say gym as a clipped form of gymnasium. That is an example of back clipping, where the back part of the original word has been clipped. In gymnasium, nasium has been clipped, and we now only have gym. So that is an example of back clipping. Um, what else? We also have fore clipping. In fore clipping, what we have is, see, let's take the example of phone. So we say phone is an abbreviated form of telephone. So here the front part, that is tele, that is being clipped, and we have phone remaining. So phone, here this is an example of fore clipping. Another one would be that of mixed clipping, where we also clip something from the beginning, we clip something from the end, and we get a shortened word. For example, flu, we get that from influenza, where in the beginning in is getting clipped, and at the end also some part of the word is getting clipped. So this is an example of mixed clipping. These are the common forms of clipping. um, So, one more thing to discuss is one of the questions was what are abbreviations? So abbreviations can also be considered as a word formation process, and it can be of different types. So abbreviation is a very broad category. Under that, we can have blending, we can have acronyms, all these things where we are abbreviating, where we are shortening a part of the word. They come under abbreviation. So one more question that was asked in the live session was on etymology. Um, so I don't think etymology has been uh, covered in the lectures as far as I know. But so etymology is more concerned with um, how the semantics of a word has evolved over time throughout history. And morphology is concerned about the word formation processes, and the constituent morphemes. So that is a brief discussion on etymology and morphology. Um, um, and so these are the practice problems. Maybe we'll discuss a few more things from the slides. So we have some time. Maybe we can discuss. So here we have just to clarify. So here, here as mentioned, so morphology is studies the internal structure of words and how words are built from smaller meaningful units called morphemes. So we were previously discussing the word cats. Here dogs is given. So in dogs we have two morphemes, dog and s. Dog would be the stem or the root of the word. S would be the plural marker that you can observe on nouns. So here one thing we can observe is that how each of the morphemes is carrying some meaning. So if we take this word unladylike, it has three morphemes. Un, lady, like. So un means not. It's sort of indicative of an antonym, the opposite meaning. So like it happens in unhappy. Unhappy is like you're not happy. So like that, un here means not. So it's a morphological prefix that means not. Lady means a well-behaved woman. So here, lady is the root of the word. It carries the um, core meaning, and those are modified based on the prefixes and suffixes that are present. And like means having the characteristics of. So, for example, when we say human like means like a human, having the characteristics of a human. Ladylike means having the characteristics of a well behaved woman. Whereas now that if we have unladylike means uh, it's the opposite. So, not having the characteristics of a well behaved woman. So, these are these are how morphemes carry meanings. So, this is an example of form and meaning, how are there, they are present in a word. So here, what are allomorphs? Allomorphs are variants of the same morpheme, but they cannot be replaced by one another. So here we see, here unhappy, un carries the meaning of opposite. Incomprehensible, here again the prefix in carries the similar meaning. Same for impossible, irrational. All these un, in, im, all these things are prefixes which have the sense of opposite. But so unhappy is a valid word, but unhappy is not valid. Similarly, uncomprehensible is not valid word. Incomprehensible is the right word. So as mentioned, so these are variants of the same morpheme, but they cannot be replaced by one another. So that is what allomorphs are. So what are free and bound morphemes? Um, Bound morphemes are words which cannot independently exist. They need to be attached or bound to another word, and only then uh, only then they can appear within a word. So for example, in dogs, S, the morpheme S is a bound morpheme. Similarly, in quickly, this ly, is a bound morpheme. Whereas if we talk about free morphemes are morphemes which can appear as a word by itself. Um, so, and they also combine with bound morphemes. So, for example, in houses, house is the free morpheme. Walk is the free morpheme. So, stems and affixes, we in the practice problems we discussed about stems and affixes. Here, let's take it up once. So, what are stems and affixes? Stem is the root. So, for example, we were discussing about regularity, right? Regularity was one of the words in I think question one. Regular was the stem or the root. So, so stem or the root that carries the core meanings. That is the core meaning bearing unit. Whereas affixes are like they change the meaning or they add grammatical function to the root word. Okay, so that is the difference. Um, so, what is the difference between content and functional morphemes? Content morphemes, as the name implies, they carry some semantic content. For example, we see over here car, able, un. Able means whenever you add the suffix able to anything, it means the ability of doing that. So when we saw the example as well, right? Um, Available was there, right? In the first question. So available means the ability of being available, the ability of availing something, or the ability of the ability of using something. So that is what available is. So here able, the suffix able has some semantic context associated with it. Now, if we talk about un is again, it carries the meaning of being opposite. That is un. Whereas functional morphemes would be, they are the ones which carry grammatical information. For example, one common example that I have been giving is that of cats. You also saw dogs, all these things. And so the S, the plural marker, that is a functional morpheme since it carries the grammatical information. So it carries the number, a number that is marked on a noun that is carried by this marker, plural marker. So any word that has this marker, it indicates that the number associated with that noun is plural. It indicates plurality. And here we have another is, so it could also indicate third person singular as well. So um, uh, for example, she takes dance classes. So here takes, here the S that is here. So that is again like, so that is an indicative of um, third person singular. Mm, we still have time, so we'll discuss some things from the lecture slides. So just a minute, I'll just search a topic to discuss. So I think a question was asked from here during the live session from hidden Markov model. So I'll just quickly discuss this. In hidden Markov model, what do we have? Um, so um, so we need to understand that when we talk about hidden Markov model, here there are some states which are hidden and there are some output which is observable to everyone. So an example where we use hidden Markov model is that of pure tagging. So in pure tagging, what are the output symbols? What is observable to everyone? That is the words. And here the hidden state would be the pure tags. Pure tags which are emitting the words or generating the words. So this is a distinction. So in normal Markov models, so we only have the output symbols which are themselves the states, and so there's no separate distinction between hidden states and output symbols in a normal Markov model, but the distinction exists in case of hidden Markov model. Mm. So in hidden Markov model, we have a set of states which are the tags. So tags are the hidden states, and the output are the words which we can observe, and words are being emitted by the tags. We have an initial state which is the beginning of a sentence. We also observe this in the practice problem. Then we have state transition probabilities. What are the probabilities of transitioning from one hidden state to another hidden state? That is probability of transitioning from one tag to another tag. And what is the symbol emission probability? So here's probability of wi given ti. So what is the probability that the tag or the hidden state ti will emit the output symbol wi? That is what it means. um, so here we have the state graph. We observed and discussed this in the problem also. We had a problem on HMM, so we discussed this there. Um, so we'll take a 2 minute break and then we'll discuss the smoothing techniques and then we'll conclude the session. So we'll take a 2 minute break now, and then we'll start. So let's discuss Kennesaw knee smoothing. So here the intuition is that let us again consider the Shannon game. So here we take the sentence, I can't see without my reading, then dot dot dot. So here we have to predict the next probable word. So say we are given two options, glasses and Francisco. So from here, how do we understand which is a better option? So we know that glasses is a better option, but we need to make the prediction, or the language model needs to make the prediction based on the corpus, based on the statistics that is there in the corpus. So say the corpus that we have, that that is about, say, San Francisco. Okay, so given that, or like say just a second. So San Francisco is like, so say it is about America. So America, and it is um, it has multiple um, what just a second. So imagine that the corpus is the about America. So it contains multiple instances of the word San Francisco. So obviously Francisco also occurs a lot uh, a lot of times in the corpus, um, but it occurs along only with San, does not occur with any other word in the corpus. So the probability of occurrence of the bigram San Francisco is very high, but probability of occurrence of reading Francisco as a valid bigram in the corpus, that is not a uh, that is not a very that's a very unusual bigram to observe. So here, but however, since this is about USA, the occurrence of glasses in the corpus would be not as high as Francisco. But one thing to note that glasses will occur with, uh, like, uh, will occur in different instances of bigram. For example, Francisco can only occur with San, so San Francisco would be the only possible bigram where. Uh, the bigram ending in Francisco, whereas for glasses there could be many things. There could be reading glasses, um, uh, 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 window glasses, or sunglasses. There could be many possible things. I don't think window glasses is a valid thing, but like sunglasses, reading glasses, all these are um, valid biograms that you can observe in the corpus. So here you see that glasses uh, is a word that is ending many different biograms. So, and it is not specific to a single bigram. It is not associated with only a single word, as it is the case with Francisco. So that is the intuition mainly behind Keneson smoothing that we use. So in the corpus, Francisco would be more common than that of glasses, as we discussed, because it's a document based of um, USA, or it's a document on San Francisco because of that. But Francisco mostly follows San and not any other word in the corpus. So when we were predicting probability of W, so in the last smoothing technique that we discussed was absolute smoothing, absolute discounting, interpolation. So here, when we're interpolating, we have simply taken the probability of the word, right? So here, where we are using this continuation probability, so instead of simply taking the unigram probability of the word, which in this corpus would be very high for Francisco, Francisco would have a higher unigram probability than glasses. So instead of taking that, can we take the continuation probability? So continuation probability would take into account how probable it is as a continuation of a word, or how likely is W to appear as a novel continuation. So given that, so reading glasses may not be in the corpus, but other words consisting of glasses could be very well there in the corpus. So that is that. So that is what means as a novel continuation. So that is what this probability computes. The probability of continuation of W, what would that be? It would simply so so uh, should this Wi minus 1 comma W, it means here W is completing the bigram. Wi minus 1 W. So here we are counting the number of bigram types that the word W is completing. So that is what it is proportional to, and then we simply have to normalize. So in order to normalize, we take all possible bigram types in the denominator, and in the numerator we only have those bigram types which the word W is completing. So this is the intuition. So in the absolute discounting interpolation that we saw just before this, so instead of taking the unigram probability, we can take the continuation probability, which is more intuitive. So if we take this, so the a frequent word Francisco, which is occurring in only one context, San, will have a much lower continuation probability. So this is the idea behind Keynesian smoothing. So one of the students had asked regarding the computation of this probability. So so given a corpus, we simply find out what are the possible bigrams that are there. All possible bigrams, not necessarily unique bigrams. First, we compute all possible bigrams that are there in the corpus. Now, once we have found all possible bigrams, we find the bigram types, which are only the unique bigrams that are present. So once I have the bigram types, now I take the count of bigram types where W is ending that bigram. So W is the second word in this pair of words. So W is ending the bigram, and what else do we take? And in the denominator, we take the count of all possible bigram types. So so that is how we get the continuation probability. So Keynesian smoothing is it's very similar to absolute discounting interpolation. So as I mentioned this while explaining. So in absolute discounting interpolation, here we had taken the unigram probability of the word Wi, and now instead of that, here we are taking the continuation probability of the word Wi. That is the difference. Mm. So what happens in back office? Say we're computing the trigram probability. So if such a trigram does not exist, if the count of the trigram is zero, we back up to the bigram. And if bigram is zero, then we back off to the unigram. So we are backing off to a lower n-gram. So that's what happens in back off. For example, we see over here probability of Wi given Wi minus 2, Wi minus 1. So this is given. So here we are estimating this. So here, say if you do not have counts to compute probability of Wi minus 2, Wi minus 1, if this is not there, so what we do is we uh, instead estimate this using the bigram probability. So what does this mean? So this is the trigram probability. How do we if we take the MLE probability, what would be there in the numerator? It would be probability of Wi minus 2, Wi minus 1, Wi. How many occurrences of this trigram is there in the corpus? So if this trigram is not there, it would have a count of 0, and as a result, the probability would also be 0. So if that is the case, we uh, we instead compute the bigram probability. Now, if the bigram also doesn't have enough counts, so here a probability of Wi given Wi minus 1, this is the bigram probability. And that would be equal to, so it would be count of Wi minus 1 Wi in the numerator. So if that bigram is also not there and it has a count of 0, what we do is we now use the unigram probability, which is probability of Wi. So this is the idea of back off. And whereas in interpolation, what we do is simply mix all the n-gram probabilities. We mix the trigram, bigram, uh, trigram, bigram, unigram probabilities, and we ensure that the lambdas they add up to 1. So that is what is an interpolation. So we can discuss good Turing. We can discuss good Turing and absolute discounting interpolation. Um, let's discuss this. So these are advanced smoothing algorithms. Um, Previously, we had also studied about Laplace smoothing or advanced smoothing, case smoothing. Um, all these we had seen, I think, in last week two's um, lectures. Um, so now we'll discuss the advanced smoothing algorithms. So We discussed the Kenusane. We'll discuss good Turing now. So good Turing, what is the main intuition in good Turing? So we use the count of things which we have seen once to estimate the count of things we have never seen. So this is the most important thing that is there in good Turing. So here, hmm, so here an important thing in here is NC. NC is the frequency of C, which means um, so frequency C means a word occurring with frequency C, and frequency of C means how many words are there which are occurring with frequency C. That is what it means. So example, here are some sentences that are given. Now if we count NC, we see that for all these words, I am here, who would like. So these are the types, the unique tokens that are there in the um, corpus of the example sentences. And if we compute their counts, so what are the number of times they have occurred? So we see I has occurred 3 times, am has occurred 2 times. Here who would like has occurred 4 times. Okay. So here we see that. So what would be N1? N1 is what are the number of words that have occurred with frequency 1. So here we have 4 words. Here who would like. So we get 4. What is N2? N2 is number of words which have occurred with frequency 2. That is only 1. And what is N3? What is the frequency of words that have occurred with frequency 1? Sorry, frequency 3. Sorry, frequency 3, and that is 1. Um, and that is the word I. So now this is the formula and idea behind good Turing estimation. So what is the idea? The idea is that we reallocate the probability mass of n grams that occur r plus 1 times in the training data to n grams that occur r times. Okay. So this is mainly done so that we can reallocate the probability mass of engrams that they're never seen once the with engrams that sorry, my mistake. So here so the main idea is that we reallocate the probability mass of engrams that were seen once to that of engrams that were never seen. So mainly this is the uh, main thing. So in order to generalize that, we have the first point. Okay. So so we take the adjusted count. Uh, so this I'm just briefly going over the points. All these things were discussed in the lecture, so I'm not being very elaborate, but I'm just touching upon the main points um, and going over the slides. So for each count C, an adjusted count C star, how is it computed? It is computed as follows. So C star would be an adjusted count. It would be C plus 1 times NC plus 1 divided by NC. So that is what you get over here. Okay. So using this you can calculate. Using this we can calculate the probability or the count of something with that has never occurred before, just by adjusting or reallocating the probability mass on things that have happened only once. So this was good Turing estimation. So, hmm. So what is the idea behind absolute discounting interpolation? So here we can observe. So when we compute the adjusted count using good Turing, here we observe that from 2 onwards, we see that so so there's a constant amount of decrease that has happened between the actual count and the discounted count and discounted or the adjusted count, and the difference is more or less 0.75 across all. So that was the idea behind absolute discounting interpolation. So that is what has been done over here, right? So instead, so this is the Emily probability. This is the Emily probability. You simply subtract minus d, and that gives you um, an adjusted probability. And with that, you simply do interpolation. We interpolate it using the unigram probability. So that gives us the formula of absolute discount. um, discuss a few more things. Um, so just a minute, so we covered a lot of topics from the lecture. I'm just searching what else we can cover. So just give me a minute. So this is an example of the output of morphological analysis. We discuss morphological analysis um, like uh, like in today only. So we saw that upon performing morphological analysis, we get the lemma, and we also get the morphological tags that are there. So here we see that. So what is morphological analysis? To take input forms like as it is given in the first column. So this would be the input and output these. So this is what is morphological analysis. So the output contains the stem. It also has information like whether it's a noun or it's a verb, whether it's the PL stands for plural, SC stands for singular. So whether it's the past tense or whether it's the uh, so is what is that is also there. Um, in case if there's some ambiguity regarding regarding the part of speech tag or the so here the ambiguity lies in here you can see it's there in the tense, whereas here the ambiguity is in the noun. Okay, in goose the ambiguity here it's goose can be a noun, can be a singular form of a noun, whereas goose can also be a verb. So this is the output of morphological analysis. Um, what else? So, what is part of speech tagging? Part of speech tagging is given a text. You have to identify what are the part of speech um, of each word in the text. So, for example, here we have a set of words. So the boy put the keys on the table. So this is the entire sentence, and these are the words that constitute the sentence. And now we have to tag the words to the corresponding part of speech tags. So here we can see that the is mapped to determiner. So all the are mapped to the determiner. Boy, keys, table, these are all nouns. Put is a verb, and we also have prepositions. On is the preposition. Okay, so this is what is part of speech tagging. So part of speech can be open class words, which are called content words. So these could be nouns, verbs, adjectives, adverbs. So they are mostly semantic bearing, content bearing. So they have meaning associated with them. Okay, so for example, noun is a house, verb is walk, adjective is just a second, is swift. Swift is an adjective, and swiftly would be the adverb. So all these things, they have meaning associated with them. They refer to objects or actions or features, and these are open classes. That is, new words are being added to these classes of words all the time. Whereas if we take closed classed words, so those would include pronouns, determiners, prepositions, connectives. So all these are closed class words. They serve grammatical purposes, um, and so that is their function, closed class words, and they are limited in number, and they uh, so as I said, they bear grammatical functionality. Um, and so these are some examples of part of speech tags. So we have noun, verb, adjective, adverb, preposition, pronoun, determiner, and some possible examples from English. So such pure tags also exist in not all, but many exist in Indian languages as well. So there are nouns and verbs in Indian languages too. Um, so this is a very interesting example from which we can understand that why is pure tagging hard. So one word can have multiple pure tags, as can be observed from this example. So the back door, here back is an adjective, whereas on my back, here back is a noun. Win the voters back. RB is, I think, adverb. Just let me check a second. Um, hmm. RB is adverb. And then finalists promise to back the bill. Here back is a verb. So same word but different part of speech, four different part of speech in four different sentences. So this is a cause of ambiguity, and this needs to be dealt with. So a very um, this is very challenging in part of speech tag, part of speech tagging. So in the Brown corpus, it was observed that so there were 35,340 instances where it had only one tag, whereas there were 4,100 words which were ambiguous, which had 2 to 7 tags. So among these 4,100, 3,760 had 2 tags, 264 had 3 tags, um, and 61 word has 4 tags, and one extreme case is the word still, which had 7 tags, so 7 possible part of speech tags. So this is a serious concern, this ambiguity that is present. um, so we still have I think 5 more minutes. We still can discuss one more topic. We can discuss this. So, what are the approaches to part of speech tagging? One is a rule-based approach. Here, each word in the input, uh, we assign each word in the input a list of potential US tags, and then here we simply use handwritten rules, and using that, we boil it down to a single tag. So here, handwritten rules are there, maybe. For example, handwritten rules can be, say, if a word is ending with ed, ed is a very clear indication that it's a past tense, and tense is usually marked on a verb. So that is an indicator. So this could be a handwritten rule that if a word ends in ed, it is a verb. So like this, handwritten rules can be designed. And using those handwritten rules, you determine which is the purest tag of a word, and that is what happens in rule-based approach. Um, so similarly, there are statistical approaches as well. So um, so here we have about generative and conditional models. We discussed generative and conditional models. We had two questions. So we discussed uh, generative and discriminative models. Um, so here we have the hmm, so here we have the probabilistic way of doing pure stacking. We have the words capital W from W1 to Wn. So these are the words that are there in the corpus. These are what we have observed. What is hidden and what is unknown is the tags, that is T1 to Tn. So the corresponding tags are unknown, they are hidden. So how do we do this? So we discussed that HMM is a generative model. Okay. So here we can see that what we are doing is here we are using the Bayes rule as we discussed. We're using the Bayes rule, and using that we need T hat is the most probable tag for the word W. T hat is the tag among all possible tags in the tag set that maximizes the probability of P of T given W. So given the word, this is the most probable tag. Okay. And so in order to calculate that, we use the Bayes rule and we flip it. So we get probability of W given T into probability of T. Now that we can expand over here. Okay, so probability of W given T is, so again here we have again used the chain rule to go from here. So here we use the Bayes rule to go from this step to this step. Now probability of word would be common across all the tags. So that is a normalizing factor. So it won't have it won't make a difference in the argmax computation. So we have dropped it over here, and we have got probability of W given T into probability of T. And once that is there, then we simply use the chain rule and break it down to this point. Um, okay, so we have discussed the practice problems. We've also discussed different topics that were there in the slides. So we'll conclude today's session. Thank you.